Okay, let's look at resisted motion. Reminder, resistance always in the opposite direction to which you're travelling. Newton's third law, remember, forces balance. Because we're going to always resolve our things into, well, usually horizontal and vertical, it pretty much means there's only going to be three situations we need to think about. So the first one, horizontal. So there we are, travelling along the horizontal. I'm saying I'm travelling to the right, so I'll make my resultant going to the right there. But if in the horizontal direction, unless they tell me other things, the only thing I've got is a resistance going in the opposite direction. So I would end up with something like that. The resultant force is minus whatever they tell me the resistance is. We'd divide by the m and we'd come up with a differential equation. Okay. So that's one case. When it comes to vertical, there's two different cases we need to think about. The first case would be when we're travelling up. So if we're travelling up, and again I'll make the resultant vector being in the upwards direction, the direction we're travelling, we will have a force due to gravity now. That'll be in there as well, in addition to the resistance. But they're both going in the same direction. So we would end up with minus mg minus r. Again, you divide through by the mass and whatever that differential equation is, we'd go and solve. Just because we've got resistance doesn't change the physics of the situation. I mean, the greatest height will still occur when the velocity is equal to zero. I mean, that's not going to change. All those sorts of things are still the same. Downwards motion. So now we're travelling down, so I'll define down to be the positive direction. We've still got the force due to gravity, and resistance now will be in the opposite direction. So we get a similar equation, but now mg is positive because it's in the direction that we're travelling. Then we divide through by m and we get some sort of equation. But that's pretty much it. There's one of those three cases is pretty much what we're going to have. Now when it comes to downwards, we have this thing called terminal velocity. Another way of thinking about it is limiting velocity. So what happens as time approaches infinity? And one of the ways we could actually solve it is, well, it's when the acceleration is equal to zero. Let's have a look at this first one from the 2020 HSC. They gave us this little diagram. It's a 50 kilo box and it's at rest initially, but they're going to pull it along the ground with a force of 200 newtons at an angle as they've drawn in there. There's also a resistive force of 0.3. There's a normal force, and then obviously a force due to gravity as well. So they want us to show that the resistance is equal to 400. And they've given us a hint, just use the vertical forces. Okay, well here's our box. Everything other than the 200 is either horizontal or vertical. So we need to break up that 200 into its two components. So we can see, oh yeah, okay, now I can see all the vertical forces, now I can see all the horizontal. We're only interested in the vertical ones. So what have we got? We've got 50g going down. We have our resistance going up, that's what we're trying to find. And we would have 200 sine 30 because it's opposite the angle. Okay. Now I know the resultant force, or in this case I've called it the vertical force, would end up being zero. I mean, the box is on the ground. It's not like all of a sudden it's jumping up or doing something like that. So vertically, nothing's happening, if you like. So all of those forces will sum to be zero. So r plus 200 sine 30 minus 50g. Well, that allows me to now go and find r, and yes, we get the answer they're looking for, 400. So now they want us to look at the horizontal forces, and they're saying, well, show that the net force is approximately 53.2 newtons. Okay, well, let's look at it horizontally then. We're moving to the right for this one, because if we're pulling in that direction, the box would move to the right. So that's where I'll define the positive direction to be. So the forces, we would have the component 200 cos 30, but also our resistance of 0.3 r. So they would sum to give 200 cos 30 minus 0.3 r. Oh, and by the way, net force is another way of saying resultant force. It's just what do they all add up to. So my horizontal force is equal to, well, cos 30, I know that's root 3 on 2. R we've just worked out as 400. A bit of calculator work, and sure enough, we get 53.2. Find the velocity of the box after the first 3 seconds. So we now know that that resultant force was 53.2. If I divide by the mass, which was 50, I get that acceleration is 53.2 over 50. Now in this case, I want to link velocity and time. So I'm just using dv to t for this one. So dv to t, well, I hate decimals in fractions, so I've made 133 on 125. Separate the variables. It's actually a very simple integral when you look at it, because you've got dv and dt. So we'd end up with 3.2 meters per second. Okay, another question. This time we're going to project something vertically upwards. Initial velocity is just u in a resisting medium. Fancy way of saying it's got resistance. Assuming that the retardation, now retardation is a force, due to this resistance is equal to kv squared. Find expressions for the greatest height reached and the time taken to reach that height. Let's draw our diagram. Okay, we're going up, so yep, I'm going to set my resultant force to be going up. We've got mg going down. I've got kv squared, resistance, going down. I also know that when x is equal to 0, v will equal u. So let's set it up. The resultant force will equal minus mg minus kv squared. Divide through by the m. I have my differential equation. Now, the first thing we want to find is the greatest height. Find the expression for the greatest height. So I want to link displacement with velocity, so I'll use v to v dx. I've written it all as one fraction because if we're going to separate the variables, that's going to make life easier if it's all one fraction there. So dx to v, I've turned it upside down. I don't know why I bothered doing that, but anyway, it looks all right, doesn't it? So I've got mv there. There's my integral. On the left-hand side, nice and easy, just 0 to x of dx. Right-hand side, what have we got? We've got a log function, haven't we? Because v is like the derivative of v squared or some multiple of it. So I create the derivative on top. I put 2kv on the top, but of course that means I need to put 2k out the front. Notice I also got rid of the negative by swapping the limits around as well. So I've made it going from 0 to u. We get the log of mg plus kv squared. Why didn't I put absolute value signs there? Well, v squared is going to be positive. K, well, I guess I'm assuming k is a positive constant. M is certainly positive, G is positive. So I don't know, I really needed the absolute value signs on this one. But anyway, we do our log laws and we end up with this beautiful expression. M on 2k, the log of 1 plus ku squared on mg. Okay, there's our greatest height. It also asked us to find the time it took to get there. So back to my differential equation, but this time, because I want to find the time, I'm going to rewrite acceleration as dv to t. So I'll end up with a different integral now. When I separate those, I now have an inverse tan function. I like the inverse tan just to be v squared rather than kv squared, so I've done a division by k, which is really a multiplication by k, because of fraction on fraction, which means out the front I need to have m on k. Just be careful with that one, that you get the k's in the right spot. But we've ended up with inverse tan, so we have 1 on a. Well, a would be the square root of mg on k. So 1 on a is k on mg, inverse tan, that same square root, but times v. Sub in the u, sub in the 0. I've also multiplied those constants together. I've ended up with root m on kg. Inverse tan of 0 is 0, that's nice. So I have this one, root m on kg, inverse tan, root k on mg, u. So there's our time. That's the thing when we're not using numbers, you come up with some wonderful expressions for time and distance. Let's do one where we're dropping it from a height. So 5 kilos, dropping from a height, gravity is of course g. We're assuming air resistance is proportional to speed, and that constant of proportionality is 1/8. We want to find its velocity after time t. Okay, let's get our equation. There we are. We're going down now, so I'm defining down. They told me mass is 5, so I'm going to say 5 times acceleration there. Gravity, so 5g. Resistance in the opposite direction, 1/8 v. So there's my equation, divide through by 5. We're trying to find velocity and time, so v to t is what we'll use. And we've got a log function. Okay, so we get minus 40 log 40g minus v, sub in the v, sub in the 0, and I've ended up with 40 log 40g on 40g minus v. If they want the velocity after time t, I've found the time after velocity v, so I now need to make velocity the subject of this. Okay, so t on 40 is the log of 40g on 40g minus v. Exponentialize, multiply out, few steps there, but eventually we get it. So velocity is 40g outside of 1 minus e to the power of minus t on 40. The terminal velocity. So there are 2 ways we can do it. As I said, terminal velocity will occur when the acceleration is equal to 0. So I can simply solve acceleration equals 0 and I get 40g. The other way, because I've got the velocity time equation, I can say, well, I know terminal velocity is the limit as t approaches infinity, and if I look at velocity, I've got that backwards exponential, and I know as t approaches infinity, that'll approach 0, so therefore I end up with 40g. So 2 different ways you could work out terminal velocity. Distance, it has fallen after time t. Okay, so we now know this, dx to t. Distance after time t, okay, I want to link displacement and time. So we'll write velocity as dx to t, separate the variables, do our integration, sub in and look at that for an expression. X is 40gt plus 1600g e to the power of minus t on 40 minus 1600g. Oh yes, this was a nice question. So the 2020 HSC, it had this pulley question. Now, first thing you had to do is basically find acceleration, show that v to t is that. There are 2 masses in operation here, so let's investigate each. First of all, on the left mass, force due to gravity, its mass was called 2m, so I end up with 2mg. Kv, the force due to air resistance. Now, this is where you had to be careful, because notice they've told you which direction the system's going. Therefore, that left-hand one is going up. That's why I've put the resistance going down. Got to be in the opposite direction. But we would also have tension in that string. So there's our left mass. So playing around with that, the resultant force, remember mass is actually 2m for this, so 2m acceleration would equal tension minus 2mg minus kv. Now let's have a look at the right-hand mass. 4mg, its mass was 4m, it said. So 4mg going down. The resistance on this one would be going up, because that mass is going down. So kV. Tension is also there. So that one we get 4mx double dot equals 4mg minus t minus kv. Remember, we're trying to find acceleration. Well, over on the left-hand side, I could make t the subject. And then I could go and substitute that into the right-hand side, because the acceleration is going to be the same for both objects, because it's all one system. So subbing that in, we end up with, and there it is, acceleration is mg minus kv over 3m, which is the expression that they're looking for. I just swapped the g and the m round so it matched what they said. I have no idea. Why did they write it as gm and not mg? Everyone writes it as mg, but well, I don't know. Given that velocity is less than gm on k, show that when time is that, the velocity of the larger mass is gm on 2k. Okay, so we've now worked that out. Separate the variables. What do we got? That's a log function on the left, isn't it? We get the log of mg minus kv. I did put absolute value signs around this one because I wasn't sure whether that was going to be positive or negative because of that subtraction. So we're going from v to 0. That's going to equal log 2. So the log of mg on mg minus kv is the log of 2. But hang on, They gave me that bit of information that V is less than mg on k. So if that is true, that fraction has to be positive. So I don't have to worry about absolute value. That one's fine. So that means I can simply say, well, mg on mg minus kv must be 2. It couldn't be negative 2. Making V the subject, we get that it's mg on 2k. And let's now look at last year's. We've got an object of mass 5 kilos on a slope, inclined at 60 degrees, so they've given us all the information there. As well as gravity, the object's acted by 2 forces, one of magnitude 2v newtons and one of magnitude of 2v squared newtons, both acting up the slope. Let's draw a picture. They want us to find the resultant force down the slope. Okay, so there's my object sitting on a slope of 60 degrees. There's good old Bob. Force due to gravity, 5g. Up the slope, I'll just combine them into one resultant force. And I'll say, oh, well, it's 2v plus 2v squared. We would have a normal force. It's in contact with the plane, so there would be a normal force as well. So, okay, they're my 3 forces. They've sort of given me a hint by saying, show the resultant force down the slope. So it's like that question the other day where we said, okay, we're not going to look at vertical and horizontal. We're going to look at down the slope. Advantage that means the normal force won't come into play because it's at right angles to it. But it does mean I'm going to have to resolve my gravity into 2 components. So there we go. We draw our right angle triangle in. Work out where 60 degrees goes in that picture. It's down the bottom. So all right, I now know that resultant force down the plane would be 5g sine. It's opposite the 60. But then it'll be minus the resistive force. Okay, sine 60 is root 3 on 2. Sine 60 is root 3 on 2, so we've got the answer. There is one value of V such that the object will slide down the slope at a constant speed. Find this value, and to make life easy, they've said, we can let g equal 10. This makes the maths a bit nicer. If it's going down the slope at a constant speed, its acceleration must equal 0. So back to the formula we just worked out, if acceleration is 0, that means 5 root 3 on 2g minus 2v squared is 0. They said we could take g equaling 10, so sub that in, and I've basically just got a quadratic equation to solve. Okay, 4 plus 200 root 3, but they want a decimal approximation anyway, so the fact that I've got a square root of a square root's not a big deal. Plus or minus over negative 4, which one is it going to be? It's got to be the positive one. Because it's in the direction we're travelling would be positive velocity, not negative velocity. So we end up with 4.2 metres per second for that one. Okay, so a couple of exercises there for resisted motion.